When reviewing legacy project drawings, you might frequently encounter transformers with the Yyn0 connection. However, in modern industrial and residential low-voltage distribution systems, the Dyn11 connection has almost entirely taken over as the industry standard. In this video, we will perform a deep dive into the technical advantages of Dyn11 over Yyn0, and explain exactly why the modern grid has effectively phased out the Yyn0 connection. In a balanced three-phase system, the instantaneous values of the fundamental frequency are symmetrical. But for the third harmonic, the situation changes fundamentally. Since the frequency is tripled, the phase difference must also be multiplied by 3. The three-phase voltages have equal magnitudes. As we can see from the phasor diagrams, the third harmonic components of all three phases are perfectly in phase. Only one overlapping pointer, and it rotates at triple the fundamental frequency. A delta connection links the windings head to tail to form a closed loop, according to KVL. These third harmonic currents circulate freely within the delta winding. The third harmonic is effectively trapped inside the delta winding and remains invisible to the external grid. The induced voltage remain pure sine waves. In a Yyn0 connection, the primary side lacks a neutral path. Without a return loop, the third harmonic currents cannot flow. Consequently, to maintain the magnetomotive force balance, the magnetic flux is forced to contain significant third harmonic components. The induced voltage waveforms undergo significant distortion with relatively high THD, which threatens the insulation life of the windings and sensitive equipment. According to the IEC 60909 standard, the calculation for a single phase-to-ground short-circuit current is defined as: here, Z1 and Z2 are typically equal to the transformer's short-circuit impedance, Zk, while Z0, zero-sequence impedance, is the critical differentiator between Dyn11 and Yyn0. According to experimental data from IEC 600768, for a standard three-phase three-limb transformer, in Yn connection, Z0 is extremely high, often reaching approximately 60%. In Dyn connection, Z0 is very low, typically between 0.8 and 1 Zk. Now let's run a simulation of a single phase to ground. By setting the zero-sequence impedance to 6% for Dyn11 and 60% for Yyn0, we can observe the following characteristics from the simulation results. 1. Voltage displacement in Yyn0 connection. The voltage of non-faulty phases rises sharply, approaching line voltage levels, which can devastate single-phase equipment on the same bus. 2. Protection sensitivity. The low Z0 of Dyn11 results in a much higher fault current. This allows the magnetic trip of a circuit breaker to react instantaneously. On the other hand, the fault current under Yyn0 connection is significantly restricted in long-distance cable supply circuits. This forces us to install additional RCDs to ensure tripping sensitivity, which ultimately increases both complexity and overall costs. In modern distribution, load imbalance is inevitable. This creates a return current in the neutral wire, which leads to a neutral point displacement voltage. U0 equals I0 times Z0. I0 represents the zero-sequence current, which effectively accounts for the unbalanced current in the system. We have just mentioned that Z0 of Dyn11 is minimal and of Yyn0 is massive. This leads to two major differences. 1. Voltage instability. In Dyn11, the neutral point remains extremely stable even under 50% or higher load imbalance. Phase voltage fluctuations are negligible. While in Yyn0, under load imbalance, the neutral point floats or shifts severely. For the heavily loaded phase, the voltage drops significantly, resulting in dimming lights and insufficient motor torque. Conversely, the voltage of the lightly loaded phase rises sharply, which can easily burn out single-phase electrical equipment. 2. Thermal loss. In Yyn0, because of no neutral path, eddy currents induced by the zero-sequence current within the metallic structural members lead to localized overheating. This thermal stress significantly shortens the transformer's operational lifespan. In the mid-20th century, the load profile of distribution grids was relatively simple, dominated by balanced three-phase motors and linear loads. At that time, Yyn0 was the preferred choice, primarily because it was easy to manufacture and cost-effective. Today, with the rapid advancement of semiconductor technology, non-linear and single-phase loads have become ubiquitous in our daily lives. This shift has led to higher harmonic content and stricter demands for system reliability. The superior characteristics of Dyn11 have naturally made it the mainstream connection in the industry. The transition of Dyn11 is essentially an inevitable result of our heightened power quality awareness and the continuous enhancement of safety standards. Here is the conclusion of this video. I hope this deep dive helps you feel more confident when choosing your next transformer configuration. As usual, we still have the final part to help everyone review our technical terminology.
Distortion. Distortion. The alteration of the original shape of a waveform. In power systems, it typically refers to total harmonic distortion where the voltage or current deviates from a pure sine wave. Harmonic. Harmonic. A sinusoidal component of a periodic wave having a frequency that is an integral multiple of the fundamental frequency, for example, 150 Hz or 180 Hz for a third harmonic. Zero sequence. Zero sequence. One of the three sets of symmetrical components. It consists of three phasors equal in magnitude and with zero phase displacement from each other, typically associated with ground faults. Eddy currents. Eddy currents. Localized electric currents induced within a solid conductor by a varying magnetic field. These cause heating losses, which are mitigated by using laminated cores.
Okay. If you have any questions or want to see specific engineering topics covered, please leave a comment. Don't forget to subscribe to the channel. This is Tech Breach. Stay curious, stay professional. See you next time.